Yeah, so let's see.
Actually,
Mike works. It's great to have Prasad continue his series from yesterday. He'll tell us about sum of squares.
Hey everyone. My apologies, I can't be there today. There was a COVID positive case this morning in my son's daycare. So I guess it's not a good thing for me to give a talk there in person, but I'm glad yesterday before the talk, right before the talk at noon, I did one of the home tests which the Simons Institute gives out. And I was negative yesterday while I was giving the talk. So that's good. Okay, so let's start. So today my plan would be, there are two lectures. The first lecture would mostly be about sum of squares SDPs, an application of them. And in the second lecture, I'll talk more about barriers and open questions. And I'll try to sprinkle in open questions as we go. Okay, so we're going to do a very quick introduction to sum of squares SDPs. So there are three questions. What do they do? We'll see what they do. How to use them will be a thing we'll focus on today. And how they work, maybe if we have time, we'll talk about it, but I doubt it. Okay, so let's see. What is sum of squares SDP? What do they do? Well, this is what happens. So if you take degree D sum of squares relaxation, and what it does is it takes as input a polynomial system. So you give it as input a polynomial system. So it's a bunch of inequalities, pi of x greater than or equal to 0 for I equal to 1 through m. Okay, and in variables x1 through xn. Okay, there are n variables and there are m inequalities or equalities in them, and we just give it to the system. And what it outputs a bunch of numbers. These numbers are supposed to be, moments of a distribution over solutions to this system. To the system P that we started with. Okay, and in particular, what do I mean by moments? You know, for every monomial, if I ask xi squared, xj, xk, it'll tell me what the expectation of that monomial is under this distribution. So it's supposed to be moments of a distribution over solutions to this polynomial system. So it's the next best thing to actually solving the system. Solving the system would be you get a solution to the system. What you get here is just the moments of an unknown distribution. Well, it's a little bit worse than that, in that these are candidate moments, in that they're really pseudo moments. There might be no distribution that actually has these moments. But this is what we get when we solve the system. Okay, and these moments, as I said, it's a number for every monomial. And you know, in order to, it's nicely, a notational thing to do is to use all these numbers and define a functional over polynomials. So here's a definition. It's just a notational simplification. Of course, it's a very powerful notational simplification. What is it? Well, you know, we have moments for every monomial, which means we can construct moments for every polynomial. So what the SOS SDP gives us, the degree D SOS SDP, it gives us a functional that can take any polynomial in at most degree D and gives out a real number. It's a linear functional. Okay. So this is just obtained by, you know, if I know the moment of every monomial, I know the moment of every polynomial, which is just linear combination of that. Okay, but what does this satisfy? Well, it satisfies the following things. Firstly, it satisfies the polynomial system that we gave it in. So meaning E tilde of Pi of x is greater than or equal to 0 for every constraint that I had. For every constraint that I had in my polynomial system, its expectation or its pseudo expectation is actually non-negative. And the second and the most important thing is that pseudo expectation of any square polynomial is non-negative. E tilde of q squared of x is greater than or equal to 0 for all polynomials, degree of q less than d over 2. Okay, so this is what we get. So you feed it any polynomial system, it gives you a pseudo expectation operator. And the pseudo expectation operator satisfies these inequalities. Okay. All right. Okay, so that's good. So now, okay, so that's what they do. So how do we use them? Well, to use them, we will see how to use them by looking at a particular application, like an example. So the example that we look at today is a robust linear regression. In particular, I'm following this paper work by Kothari, Clivans, and Meka, which I think is probably the most cleanest examples of SOSSDP being used. And in fact, we can argue about it sometime. I actually think it's much more compelling than Gomans-Williamson SDP. But yeah, of course, because Gomans-Williamson SDP has a rounding step, which is somewhat ad hoc, which just comes out of nowhere. But this is much more principled. Okay, so here's what's happening. Okay, what's the problem? It's robust linear regression. We get a bunch of training examples where xi is in R to the D and yi is in R. Okay, it's a supervised learning task. So what is but the examples come in two categories. 1 minus epsilon n of them are good points and epsilon n of them are bad points. As you can imagine, bad points are just arbitrarily adversarial. So they're just adversarial, arbitrary. And the good points are actually of the following thing. Let's say they have this following setup. The setup is a natural setup for linear regression. So what you have is xi hat, the example is a Gaussian vector. Okay, and the label is actually labeled as per a good linear function, L hat in a product xi plus gamma I, where L hat is a linear function with some bound on its norm. Okay, and gamma I is some small noise, small Gaussian noise, let's say. Okay. And let's say it's a, let's say the noise is of magnitude gamma or something. Okay? And of course, what's the goal? The goal is to find some linear function L star such that its cost on the good examples is small. What is the good examples? Basically, it's the examples from the set S. So if I look at expectation I from S of the cost of that linear function, this should be small. Okay, that's our goal. To find some linear function that fits the good points. We don't care about the bad points. All right, is the problem clear? Okay. Okay, so now we have this black box that takes in a polynomial system. So the natural thing to do is to formulate our problem as a polynomial system. Okay, and this is what we do. So what are the variables of my polynomial system? Well, it's firstly you have the linear function that you want to find. I'm calling it L1 through LD. In an ideal world, this would be the true linear function L hat, but those are the variables that stand for that. And I guess the key distinction between this robust problem and the usual linear regression is the fact that for every example, I don't know if the example is a good point or a bad point. And somehow, if I knew which points were good, it would be much easier problem. So really, we need to have a variable that tells us if a point is actually a good point or a bad point. And so let's write that. So Wi is actually the indicator that xi is a good point. Okay, I mean, of course, that's the intended meaning of the variable Wi. We'll write a polynomial system with this meaning. Okay, so now we start writing constraints of the system. So firstly, Wi is an indicator. It has to be Boolean. It has to be 0 or 1. So, the natural thing is to say Wi squared minus Wi equal to 0. Okay, the only solutions to this are wi being 0 or 1, so that's good. Okay, and then we want at least 1 minus epsilon n fraction of the points are good points, right? So that is just saying some more I wi is equal to 1 minus epsilon n. Okay. Okay, and we have a bound on the actual linear function that we're finding. We knew that the original linear function had 2 norm less than 1, right? So let's just do the same thing here. Let's just write L squared is less than 1, 2 norm squared. Okay, and finally, what we really care about is the error on the good points. Okay, so let's say the error on the good points is we want it to be at most, I shouldn't use epsilon again, let me say delta. We want the error on the good points to be at most delta. So let me write that constraint. Okay, so how do I pick up just the error on the good points? Well, I sum over all points, sum over I equal to 1 through n. wi picks out only the good points. And then yi minus L inner product xi whole squared. Okay, so that is that gives you the error on the good points. And we want it to be on average less than delta. Let's say 1 over n is less than or equal to delta. Okay, so does that make sense? Okay, so please stop me if you have any questions.
There is a question that was in the chat. I think Ilias asked, why in the second constraint is it an equality? Is that without loss of generality?
Yeah, I think we could say it's without loss of generality, as in we could say the SDP finds a linear function and 1 minus epsilon and good points that fit with it. Yeah, so that's why I put an equality. You could do most of, I think all of the proof with an inequality also. I'm just keeping things simple here. Yeah. Okay. Thanks. Okay. All right. So, okay, what do? We take this linear system and feed it into our black box. It gives us a set of pseudo moments. Okay. So let's say we use a degree 8 sum of squares SDP, and you get a pseudo expectation operator on degree 8 polynomials. And the polynomials, you should remember, are on wi and l. We are writing polynomials in, the polynomial systems, the variables are wi and l. Capital Xi and little yi are actually our data points that we got. So the algorithm has them as numbers. And of course, n and epsilon are all numbers that are there. The variables in the polynomial system are really wi and l, and you get a pseudo expectation on that. Okay, just to remind. All right, so okay, so this we get a whole bunch of these expectations or pseudo expectations of all of the monomials, and the algorithm is really simple. The algorithm is, let's just output the pseudo expectation of the variables that we care about, which is L. So output this vector L, your L star, your output linear function is e tilde of L1, e tilde of L2, e tilde of LD. Or basically, it's this e tilde of L. Okay, that's what we do now. So that's the algorithm. The algorithm is just that. You take this polynomial system, run the degree 8 sum of squares SDP on it, and you see what you get for the linear function. Okay, and this algorithm, Kotari, Klevans, and Meka show that this algorithm, the L star's error on the good set is at most like the original error that we had, like delta plus a square root of epsilon. So okay, but now let's see. Okay, so we've used it. Now, I want to see how do we analyze the sum of squares SDPs? How do we analyze this? Okay, that's our goal next. Okay, so let's see. So it turns out that the way to think about the sum of squares SDPs or reason about them is to look at the dual, and the dual has a very nice object, which is the dual of the sum of squares SDPs or semi-definite program that we're looking at are sum of squares proofs. Okay, what is a sum of squares proof? Well, sum of squares proof is just a proof system to reason about polynomial system inequalities. For example, suppose you had the following set of inequalities with you, summation pi of x greater than or equal to 0 from I equal to 1 through m. And you want to prove that these inequalities imply q of x is greater than or equal to 0. Okay, you want to prove this. And a very natural proof, which like comes from high school algebra, is to actually find an identity like this. If suppose you found an identity which looks like this, q of x is equal to sum over I of a sum of squares polynomial, sum of squares polynomial times pi of x plus another sum of squares polynomial. Okay, and what's a sum of squares polynomial? It's just what it is. It's a sum of squares. It's just ri squared of x. Okay, rij squared, but with some sum of squares. Okay, so if you find an identity which looks like this is an immediate certificate that q of x is greater than or equal to 0 whenever pi of x is greater than or equal to 0 for all I. This is a proof. And so the dual of the sum of squares semi-definite program is really looking for sum of squares proofs of polynomial inequalities this way. So in particular, to prove facts about the pseudo expectation operator, all you need to do is to prove sum of squares, find sum of squares proofs. In particular, here's the theorem, right? So, so E tilde, like, okay, suppose E tilde is a degree D pseudo expectation functional. The output of a degree D sum of squares is dp, then E tilde of q of x is greater than or equal to 0. Well, let me just state one direction of the implication right here. If you can prove pi of x greater than or equal to 0, i.e. 1 through m implies q of x greater than or equal to 0 using degree D. If there is a degree D sum of squares proof that these inequalities imply this inequality, then the corresponding pseudo expectation is also greater than or equal to 0. Okay. So if you want facts, well, basically pseudo expectation is talking about pseudo moments. There's a pseudo moments and a pseudo distribution. If you want to prove facts about this pseudo world of pseudo moments and pseudo distributions, or whatever facts that are true there, the only way to prove them is via proving the fact using a sum of squares polynomial. So by sum of squares proofs. Okay, so let's see how this goes. An example would be good. Okay. So let's say you want to prove that wi is less than 1. Okay, I've pasted the polynomial system that we are using on the left. So this is our sort of our axioms of our system. Okay, with which we start all our proofs with. And suppose you want to prove this inequality, wi less than 1. Well, here's a proof. You could say 1 minus wi is equal to 1 minus wi whole squared plus wi minus wi squared. Okay, just an identity. And this is an SOS polynomial. And this is one of your axioms. Right, so this is a proof that this is greater than or equal to 0. So we prove that 1 minus wi is greater than 0. So this is just algebra, right? Right now, this is just high school algebra here. But what happened is because of that, we actually have a conclusion now. E tilde of wi is less than 1. Okay. Okay, and then similarly, if you want to prove wi is greater than or equal to 0, this is even easier. You say, oh, let's say, look at wi is equal to wi squared. And so therefore, this is greater than or equal to 0. So therefore, wi is greater than 0. Okay. please stop me if you have any questions. And so the real power of sum of squares SDPs is that it brings in all the power of high school algebra, inequalities, the way you can simplify just algebra into analysis of SDPs, right? Instead of thinking about vectors and geometry, now you're just doing high school algebra to sort of simplify things. So it's very powerful. So let's see. So suppose I want to go back to what we wanted to do earlier. What did we want to do earlier? We want to understand the error on the good points of the output linear function. Remember that we output the linear function e tilde of L. That was our output linear function. So let me write down what the error on the good points is. So for that, it's actually convenient to define some notation. So let wi hat be the, what is wi hat here? It is the indicator that xi is a good point. Okay, so we have an indicator function for xi being a good point. So let's see what is the error on the good points. Well, you sum over all the I equal to 1 through n, and you say wi hat times yi minus the thing that you output, e tilde L. This is your function that you output. This is the error, yi minus e tilde L xi, that's the error. You square the error, and you sum it up over all the good points. Okay, so wi hat is an honest to God 0, 1 number. It's just a definition. But L is a variable, and yi and xi are really also numbers here. Okay? Just to keep track of what's a variable, what's a number. Everything looks like a variable here. So okay, so now how do we go about simplifying this? Well, the thing is, our only tool at hand is sum of squares proof. So every step we do, we have to justify using a sum of squares proof. Okay, but so here's one fact about pseudo expectations, which you can prove using sum of squares proof. It's the pseudo expectation Cauchy-Schwarz, which is e tilde of a polynomial squared is at least e tilde of the polynomial whole squared. Okay, this is a pseudo expectation Cauchy-Schwarz. This is just you can this is just an inequality. It's true, and let's take this for granted now. It's a Cauchy-Schwarz inequality. If it was true expectation, of course it's true. For pseudo expectation, you have to prove using sum of squares proof, but you can do it. Okay, so what that lets us do is it lets us move this pseudo expectation in here out. Right, so we just say this is at most pseudo expectation. Actually, let's move it all the way out. Sum over I equal to 1 through n, wi hat yi minus L in a product xi whole squared. Okay, so that's good. All right, so then, okay, so what do we do next? Well, the thing is, it's going to be an algebraic proof, and we have to use the axioms that we have, and therefore let's just proceed and see how to get to our axioms that we have. So the thing I'll do is I'll introduce wi plus 1 minus wi in here in the middle. Okay, that's just something. So I'll get two terms now. So I'll get term 1, which is e tilde of sum over I, wi hat, wi times the error term, y minus L in a product xi, the whole squared. And that's term 1. And then there's another term, which is e tilde of sum over I, wi hat, 1 minus wi times yi minus L in a product xi, the whole squared. Okay, I get two terms like this. Okay, so that's good. Okay, so now let's just bound the two terms separately, one by one. The first term is, I wrote down the first term here. And the first term is easy because, I mean, recall that wi hat is really a number which is 0 or 1, which is indicator of xi is a good point. Okay, it's not a variable. So in fact, if I look at this first line here, there is a number wi hat here, which is 0 or 1. If I drop it, I'll only increase its value. So I'll just drop wi hat. If I drop wi hat, I'll get a larger value. Okay. Okay, this is very nice. Why? So because now the second line here, this is exactly corresponds to one of our axioms that we have. Okay, the axiom about what is the total error on the good points that the STP shows up, looks at. So this is really one of the axioms we have. So therefore, the second line is really n times eta. I mean, actually, I've been sort of a little bit careless with my notation. I should have stuck with eta, but now I have delta. Delta is there, so n times delta. So that's it. Okay, so this was easy. Term 1 is easy. Term 2 is where something interesting happens, or something we have some little bit of work to do. Okay, again, what's term 2? The first step in term 2 is, okay, this is a term 2. I drop wi hat. Okay, that's just because I know wi hat is 0 or 1. So if I drop it, I'll only increase the value. So I drop wi hat. Okay, so that was easy. Okay, the second step is I'm using a Cauchy-Schwarz. Okay, so I'm going to use a Cauchy-Schwarz inequality. Again, I'm going to appeal to pseudo expectation Cauchy-Schwarz inequality, and I get this. So okay, please stop me if there's any questions. I haven't checked. Okay, there are no other questions. Okay. Okay, so this is what we need to bound. I applied a Cauchy-Schwarz inequality. Okay, so the first term, summation over I 1 minus wi squared. Well, what is that? You can expand it out. It's sum over I 1 minus wi 2 wi plus wi squared. Okay, and then you expand it out. This is exactly equal to epsilon n. Okay, because of this polynomial is exactly equal to epsilon n because of the constraints, the axioms, because of axiom 1 and axiom 2 together, they just imply that. Okay, so it's really the second term, which is interesting. Okay, so what happens in the second term? Okay, so in the second term, first thing I'll do, I will maybe I'll just drop the wi. Okay, because okay, what do I need in order to drop wi? I need wi squared less than 1. Yeah. Yes.
Where's that wi squared actually coming from in that second term?
I'm sorry, we couldn't hear.
Where is the wi squared in the second term coming from? I mean, you had.
Oh.
Schwarz. I don't see what.
Oh, right. Yeah, okay, that's even simpler. Thanks. Yeah, so there isn't. Yeah. Okay, yeah, that's what I should have done. Yeah, okay, good. Yeah. Thanks. Yeah. Yeah. Okay. So that's yeah, good. Okay. So now we just need to bound the second term, and first thing we'll do is we'll just use the inequality, the simple inequality, a plus b whole to the 4 is smaller than 4 times a to the 4 plus 4 times b to the 4. Right? Yeah. 4 times a to the 4 plus 4 times b to the 4. So that means that I can just expand this out. I get 1 over n sum over I. Okay, first thing is, yeah, all right. There was this little bit of subtlety here, which I should have been careful. Okay, so I didn't really drop the I. So remember, I was sum was over all 1 through n. Initially, the sum was over all 1 through n. And then I don't really drop wi. I actually keep wi hat. So I'm just going to write this as I over the good set S, because wi hat picks out really the good points. So it's really the I over the good set. Okay, so now what do I have? I have an average over the good set. Okay, an average over the good set of yi to the 4 plus L in a product xi to the 4. Okay, this is what I have. Of course, there's an E tilde here. E tilde here. Okay, this is what I have. So the key point is it's an average over the good set. Okay, because it's an average over the good set, all the random variables are very well behaved. In particular, capital Xi is a Gaussian. Yi is also a nice Gaussian, right? So in fact, you can bound the norm of all of these quantities here, right? What is the average over the good set? Average over the good points of yi to the 4 is like taking a standard Gaussian, taking n copies of it, averaging it. So the first term is order 1. Okay. The second term is a little bit more subtle because it's you're not averaging a number, you're averaging some pseudo expectation, but pseudo expectation is linear. So let's just talk about this quantity is a pseudo expectation of the average polynomial. Okay, what is the average polynomial of average over all Gaussian space? Let's say average over all Gaussian space of L in a product X whole to the 4. So here what I did was I just replaced the average over and the good set, assume there's enough samples, there are lots of good points. So as you replace the average over the good set by average over the Gaussian space of this quantity, if you have sufficiently many samples, that won't be a problem. And then what is this polynomial? As a polynomial, this is actually equal to norm L whole to the 4. Sorry, 3 times norm L whole to the 4. That's what that polynomial is exactly equal to. Okay, so right, so that's good. So now we have E tilde of 3 times norm L whole to the 4. Okay, and we already assumed that norm L squared is less than 1. So that's part of our axioms. One of our axioms, norm L squared less than 1. Therefore, this is at most 3. Okay, so the whole thing is you have an epsilon to the half times an order 1 quantity. So you get order square root epsilon. And the square root comes because of the Cauchy-Schwarz. Okay, so that's the whole analysis. So the key point that sort of I want to drive is, I guess there are 2 points. One is, of course, that you got the entire all the power of high school algebra into analysis of an SDP, which is very good. And the second thing is that what we did over here is also something conceptual in that, in some sense, if you had a black box that actually solved polynomial systems, like a magical box that solved polynomial systems, okay? And then if you fed it the polynomial system that we wrote down for linear regression, right? The polynomial system that we wrote for linear regression, okay? Then at least in the, even at least in that case, we should be able to prove that the output is what we want, right? We'd have to prove that L star is close to the true linear functionality. Otherwise, we did something wrong when we wrote the linear polynomial system. Okay, so it should at least be true that the polynomial system correctly identifies the linear function. Okay, this is identification. So of course you need to prove this, right? And what we just saw is that if you prove identifiability, if the proof of identifiability is a degree D sum of squares proof, then is a degree D sum of squares proof, then the degree D SOS SDP works in finding it. SDP finds the link, so that's the power of this. So really, in some sense, you're doing what you naturally have to do, right? You naturally have to prove things, right? And all we're saying is you just tie your hands and use a sum of squares proof, then your SDP also proves the same thing internally and gives you the right answer. Okay, so any questions on that? Okay, so this is a very powerful paradigm. It's been used in lots of problems for robust statistics. Okay, so that I think completes the discussion of or the demo of one example of sum of squares SDPs that I wanted to show. Hopefully, you have a sense of what sum of squares SDPs can do. So let's proceed further. So okay, so the next thing I want to talk about is I want to suggest some open questions and research directions broadly in this area in algorithmics. And I think one of the very compelling research direction actually is to mix local and global algorithms. So this is a, what do I mean? So firstly, if you look at local algorithms, what are local algorithms? I would put BP, AMP, and something even simpler, like what's a simpler one? Tree recursion. What's a tree recursion? Well, in stochastic block model, for example, if you had, let me show what a tree recursion thing is. I guess what I mean is, in stochastic block model, if I have a vertex and its neighborhood looks like a tree. Okay, now suppose I told you the labels of the leaves of the tree. Okay, suppose I told you the labels of the leaves of the tree, then there's an immediate Bayes rule, or you can use, or just a Markov property, lets you figure out the marginal of the root. Right? It's just very easy to figure out the marginal of the root. So this, I'm calling it a tree recursion algorithm, because it's somehow, there's some algorithmic thing you have to do. Given the leaves, you have to compute the root, and it's a simple thing, but it's still some local thing. Okay, so these are local algorithms. What would I call a global algorithm is spectral or SDP. Okay, so what are these? Well, we saw what spectral algorithm, non-backtracking walk, and SDP. And the key point here is that here, when we say BP, I mean constant number of iterations of BP. And this is, of course, spectral and SDP. Okay, so now what is true? Well, typically we know how to show BP converges or AMP converges only when we have constant correlation with the true answer. Somehow in a neighborhood of the true answer, or with constant, like if you start at a warm start, where you start with constant correlation with the true answer, then you can show that in constantly many steps, you get to the optimal answer. Whereas spectral and SDP, if you look at spectral, the way it works is you use power method. When you do power method, you start at a random point. Right? It's a random starting point. Or in some sense, you don't need any special starting point. It's a full-fledged algorithm on its own. Okay, so whereas in a warm start, you need to find the warm start. Okay, and what is the advantage of local algorithms? Well, local algorithms are really trying to use all the local probabilistic structure that is there, right? In particular, in this tree and reconstruction, you really know exactly how the nodes inside the tree should behave given the neighborhood, right? And the local algorithm will try to, respect that and figure out the marginals based on the local roots, right? So therefore, it's somehow, you could say it's optimal. It does sort of the optimal thing to do in a neighborhood. Okay? Whereas if you look at spectral or SDP, it's very far from doing that, right? It's it has it doesn't really, it's not clear if it does something optimal locally. So in particular, it seems to be that if you want to solve, I guess one open question would be, how do you get optimal recovery in SBMs? If you want to solve this, it seems like we have to mix local and global together. Local and global would have to sort of work together. Right, and so this, in fact, I guess a really compelling open questions to find: do optimal recovery in SBM? Of course, there's a caveat here. The caveat is that maybe optimal recovery in SBM is actually hard to do, but maybe in some cases it's easy, and we'll even to get started on it. It seems very tricky. So
probability of error.
Sorry.
The optimality here is the probability of error is optimal.
All right, optimal. Right. The optimality is the correlation with the true planted community.
Okay.
So, yeah. So you want to maximize the correlation with the original planted community that you had.
And it's to community or any number.
I'm sorry.
Two communities, number of communities.
Oh, right. Yeah. So I mean, you'd want to start doing it for two communities, and for greater number of communities, there is a chance that there are, even for two communities or higher number of communities, it's not clear if it should be completely tractable to find the Bayes optimal solution. But I mean, it could be computationally intractable. But we are so far away from the algorithm that we don't see the barriers yet. Right? I think maybe we'll see the barriers as we go closer, but we are so far away. I don't think we see the barriers yet. Okay, so I mean, and like this research direction, actually, I think it sort of has implications even beyond inference. Even if you look at combinatorial optimization, there are sort of open questions here, which are all related to this issue of how do you mix local and global. Okay, so what's our most favorite problem in combinatorial optimization? Max cut. Right, so max cut, we know everything, like it's 0.878. Well, of course, we don't know the unique games conjecture, but we will, so at least we know something for max cut. So then you could ask, what about bounded degree max cut? So can you get a 0.878 plus order 1 over square root d approximation for max cut on degree d graph? Meaning you want to beat 0.878, and in fact, you ideally would want to know how much exactly we can beat. For every d, if I ask you what is the best approximation for max cut on degree 5 graphs, hopefully we'll have an answer to that someday. But even the order of magnitude, whether it's order 1 over root d, is not known. And what is the issue here? Well, the issue is you run Gomans-Williamson. Okay, Gomans-Williamson gives you 0.878 already. Once you run it, you get 0.878. But because Gomans-Williamson is such a global rounding algorithm, it will make mistakes. So there will be neighborhoods, for instance, there'll be obviously wrong. So there'll be a neighborhood where all the neighbors are +1, and the vertex will also be +1. Right? There'll be all sorts of mistakes in this half space cut that we produce. Okay, and a local algorithm will immediately see the mistakes and try to fix it. So the obvious thing to do is run Gomans-Williamson and fix it by hand. But then we don't know how to analyze it, and so it's sort of stuck. I think so. I should say that there is work by Feige who gave an algorithm which is 0.878 plus 1 over d to the 4 for this problem. But order 1 over root d is sort of the reasonable answer here, because you can prove a hardness of order 1 over root d on degree d graphs by sampling. But in general, it comes down to this issue of how do you mix local and global. And there are some other problems where global algorithms haven't made a dent at all yet. For example, 3-dimensional matching, which is sort of related to independent set in degree 3 graphs. It's not exactly the same, but it's sort of related. For 3-dimensional matching, again, the best algorithm is a 4/3 approximation using local search. It's it's an interesting question to try to do it using convex optimization. I think that might be doable, but in general, can you push this frontier further? Question. Okay, so what are the different possibilities here? Well, one possibility is that maybe local just subsumes global. Okay, so meaning you show that BP actually just converges from random initialization, or it doesn't even have to be random, some initialization that you can compute easily. Okay, in particular, you'd hope that BP is this update given the neighbors, you compute the root. So you'd hope that it can simulate the power methods. BP should be able to simulate spectral, but I think the analyzing this for log n steps is very hard, and we don't have good ways to do this. Okay, so what is the other situation? The other situation is.
Prasad,
Oh yes.
do you know this here for SBM?
Oh no, we don't know. We don't know this for any of the models. Yeah. And the same, okay, then you could ask the reverse question. Maybe, okay, global subsumes local. Okay, so global subsumes local is, it seems, okay, seems like it should be true. Well, after all, anything that happens local is a low degree polynomial. So why don't we just encode all of the local constraints, the Bayes optimality, local Bayes optimality as polynomials in our SOSSDP and try to run it. So, we can of course add all the local constraints, local optimality, local Bayes optimality into the SOSSDP, and you can write an SOSSDP that way. Of course, but the issue is we don't know how to analyze it. I guess, but there's one success on this front where global subsuming local. It's not from inference, but in optimization, combinatorial optimization. Bansal, Gupta, and Guru Ganesh, they showed that if you use Sherali-Adams hierarchy plus SDP, you can use that to sort of get the optimal approximation for degree D independent set and degree D graphs. Okay, you can do that, but we don't. But the proof involved a lot of really using a lot of results from graph theory, so on. So we still don't know basically how to make global subsuming local in any of the contexts that I'm, stochastic block model or optimization. Okay, the more viable approach may be, okay, first you use a global algorithm, and then you use it to get a local. Then the output of the global algorithm becomes the input to a local algorithm. Okay, and this has been done in a few times. And in fact, basically the global algorithm gives you like a warm start for your BP or something, and then you do the local. And one thing, the key difficulty here is, one of the key difficulties here with using with BP is the following, that the output of the global algorithm is not a probabilistic object, right? Output of global, suppose you run spectral method and you get the eigenvector and you round it somehow. So you have some vector, plus minus one vector. You have very little information probabilistically about that vector. Apart from the globally, it's correlated with the true solution. You don't know anything locally about how the probability distribution behaves. So basically you start at a point where you know very little about what's going on. And the worst is that you somehow used up all the randomness already, because the global algorithm already looked at the whole graph and computed the eigenvector. So for a local algorithm, there's no randomness left to sort of play with, or like sort of nothing looks random or probabilistic for the local algorithm. But this issue was handled cleverly in this paper, Mosul, Niemann, Sly. So what they did was the following. So what they do is, so you have a SBM, okay? For every vertex U in the SBM, you pluck out a tree of some depth. Let's say this T sub U is a tree, okay? what you do is you run the spectral algorithm on the graph minus the tree. Okay. After you run the spectral algorithm on the graph minus the tree, you do get a ±1 cut. And it's not a probabilistic object. There's no nice probability distribution on it. But one thing is true is that the ±1 values is globally correlated with the true solution. So you get a cut X on the vertices of G minus TU, right? That is correlated with the true cut. Right? X in a product X hat, with the true cut, the correlation is like, I don't know, 0.9 or let's say 1 minus beta. Okay, there's some correlation with the true cut. Okay, and now the clever idea is, because we did not use the tree at all, the spectral algorithm did not even see the tree, local tree, the randomness in the tree is still there with us. In particular, you can think of the places where U connects to the graph as a random thing, because this graph is an SPM. So in particular, the way to sample a neighborhood of U is you start growing a tree around you, just like we saw yesterday, like a Poisson tree, Galton-Watson tree. And then it's going to attach to this graph, G minus TU, at some random location. Okay, it's random from the point of view of the spectral algorithm. In particular, what that means is you're back to, in some sense, locally in this tree, the situation looks like the tree reconstruction that we just saw. Okay, it looks like tree reconstruction with all the leaves having some noise in them. The noise coming because your spectral algorithm is not perfect. It's going to have some noise. So therefore it looks like noisy tree reconstruction. And what Moseley-Neiman-Sly are able to do is they're able to show that noisy tree reconstruction is just as good as true tree reconstruction if you are sufficiently above the case threshold. So sufficiently above the case threshold, this gives an optimal recovery, in Bayes optimal recovery. So it's a very nice algorithm. So there is another reference which I wanted to add here. Hopefully someone in the audience can tell me the reference. It's a paper by Montanari and someone I'm missing. In the context of AMP, they have an algorithm which is first global, then local. Okay, yeah. So, but this seems like a more viable approach. But the key bottleneck here is, as I said, the global object is not probabilistic. Okay, so if that's good, let me. From like. Okay, so let me move on. So here, the next thing I want to mention a couple of open questions in sum of squares lower bounds. The first open question is to prove a sharp transition in the refutation complexity, right? So we have lower bounds for SOS for planted clique. We also have nice lower bounds for many problems, I guess, 3XOR and so on. But I guess some of those transitions are not sharp. So this is one of the sharp transitions which I'm quite interested in. So here the issue, the setup is you're given a graph, which is Erdős-Rényi graph with average degree D, okay? And you want to certify the size of the maximal independent set of this graph. Okay? And of course, you can use degree D sum of squares to certify. And if you define alpha D to be the optimum of degree D SOS SDP for max independent set. Okay, so this is basically the best bound that the degree D sum of squares SDP can certify. I guess I didn't mention that.
Is the average degree D related to this degree D SOS or degree?
Oh, sorry, thanks. Yeah, I should say, sorry, yeah, thanks, yeah. It's alpha L is the degree L sum of squares. Yeah, thanks. Yeah, I fixed the degree D in the graph and asked for alpha L. as I vary L, I get better and better bounds. And one thing I didn't mention earlier is that degree L SOSSDP takes n to the L time. So in some sense, the degree of the sum of squares SDP is a proxy for complexity of the problem. So then you could plot how this, this upper bound that you certify, does it improve as you increase D, increase L, increase the degree of the service. And basically already alpha 2 is some value. And the point is that the value you'd expect, or if you believe that there's a sharp transition, you expect that the value doesn't budge at all until you increase your degree of your sum of squares SDP to something super constant like log n. In particular, the open question is that, can you prove, or is it true that alpha 2 is equal to alpha 100? Or more generally, alpha 2 is equal to alpha L for all L natural numbers. For all fixed L, is it the case that the value doesn't budge at all? This would be a sharp transition in the complexity of certifying an upper bound on the independent set. So, and that'll be nice. I think there are very few results where you have such a sharp transition. I guess one such result is I think the recent result on Sherrington-Kirkpatrick, where you can show that 2, certifying any bound bigger than 2 is hard. But here is another one which is interesting. Okay, and the other, I guess one of my favorite questions is to prove a lower bound for local statistics plus SOSSDP, like the local statistics SDP that I mentioned yesterday with the SOSSDP for Bayesian CSPs. In particular, yesterday we saw this transition where the problem is supposed to go from easy to hard, meaning whenever you have a stable, whenever the naive fixed point is stable, we believe that the problem becomes hard, right? So here's a question. When the naive fixed point is stable, prove that local statistics plus SOSSDP is feasible, even on random graphs in the null distribution. So meaning that the local statistics SDP, which is sort of the natural SDP that achieves the, it's a natural SDP that achieves the threshold, doesn't, cannot distinguish just below the threshold. Okay, and this will be, I think this will be a very good evidence, I think, for this change in complexity that we have been conjecturing yesterday. We drew all these pictures, and now we know the region where the problems are easy and we have, it'd be nice to gather evidence that the problems are hard when it's supposed to be hard. And I think this is one good way to show that the complexity of the problem does change drastically when you cross that transition. For example, K community SBM, once you cross the Kestenstigen threshold, at the Kestenstigen threshold, you don't want to prove this. And here, of course, this looks like an SOSSDP lower bound question, but it's actually also, I could also state it as a question which is maybe interesting from a different point of view. There's a natural measure on, there's a natural choice of marginals at a BP fixed point. The natural choice of marginals are given by this, I guess, the Bethe state, or there's at a BP fixed point, for any local marginal, there's a natural answer. This Bethe state, or basically, if you give me any tree, for example, I can write down the marginal distribution of the labels here. Because I know all the incoming messages to the tree, I can write down so BP, in short, BP recommends a set of marginals. BP recommends how the distribution should look like locally, okay? And this distribution kind of satisfies most of the constraints that you would want. The only thing that's hard to prove, of course, is that this set of marginals recommended by the BP is actually positive semi-definite. So basically the Bethe state, the Bethe measure, the local marginals of the Bethe measure that you can calculate, you want to prove that that is PSD. And there is hope here because I think Siddhant, somebody verified that he told me that the Bethe states, or the Bethe measure that you get here, coincides with the solution that's recommended by pseudo calibration, which is a different technique for proving SDP lower bounds. So there is a natural answer for what the SDP solution should be to prove this lower bound. And we just need to prove that that solution works. Okay, any questions?
First, let's thank Prasad for doing it.
In the problem of certifying an upper bound for a max independent set, what is the conjectured value of alpha where we get stuck?
I think alpha 2 is like 1 over square root d, and maybe I think it's 1 over square root d.
Thanks.
Incredibly, I had exactly the same question.
Two questions with one stone.
Just to see if you have perspective. For large D, the true answer is much smaller order magnitude, 2 log D over D. And so you're saying alpha 2 is 1 over root D.
Yes,
that's
okay. Yeah, and 1 over root D comes from spectral, right? Basically, this conjecture says that you can't do better than the naive spectral. So, like the alpha 2 is 1 over square root D.
1 over root D is the Gaussian weight function.
so then for max cap, it probably gives a better approximation. It's just not well suited for independence. It's probably better suited for max cap.
It's a constant weight.
Right. Also, this is, oh yeah. That's right. Yeah, I think also the issue is certification, right? The certifying an upper bound is different than finding one. I think that's the key difference here.
Any other questions?
Oh, I have a question. Prasad, can you hear me?
Yes.
It's Adam Clevens. Hey, great presentation. I actually wanted to ask you in the analysis for the robust regression.
Right.
There's some point during the analysis, I can't remember where this happens, and I didn't quite see it in your analysis, where you have to assume that epsilon, the fraction of corrupted points, is bounded, has to be bounded less than some constant, or the whole argument breaks. And then what happens is, if you want to kind of extend this to higher degree, like regression for higher degree polynomials, then that constant of fraction of errors that you can handle gets smaller and smaller in sort of an exponentially bad way. It's sort of annoying. And so I know, like, if you want to get around that for linear regression, you can use these techniques that we've both worked on for, the list decodable case. But I was just wondering, like, is there some simple analysis that can handle all values of eta, less than, basically all values of epsilon less than like a half. I think a half is the limit here.
Right.
Something like that. So sorry for the technical question.
I don't know. Yeah, I guess we shouldn't expect it, right? Because we should expect to be able to produce a list, right? As in E tilde L, for instance, could be 0. We need to change the rounding somehow to make this to work.
No, I'm saying even if epsilon is less, if epsilon's less than a half, then you should always be able to get a unique one.
Yes. But you're saying that this analysis doesn't even reach half.
Yeah. Like it needs to be less than some small constant, or something. And then it gets worse as you go up to higher degrees.
Okay. Actually, I haven't looked into that at all. Yeah. I haven't thought about it. Yeah.
Okay. Sorry.
Yeah. No, thanks. Yeah.
Great talk.
Thanks.
Excellent. So I guess let's take a 20-minute break. We'll be back here at 3:25. And thanks again, Prasad.